Hello students, in this session we will be studying about moving coil galvanometer, magnetic dipole moment and magnetic energy of a dipole. We know that an ammeter is a device used to measure current flowing through a circuit and a voltmeter is a device used to measure potential difference between the 2 points in a circuit. A current in a circuit or a voltage in a circuit can be measured in terms of torque exerted by an external magnetic field on a current carrying coil. Analog ammeters and voltmeters work on this principle. A galvanometer is an electromechanical instrument used for detecting and indicating electric current. Let us study in detail about this moving coil galvanometer. This is the top view of the diagram of moving coil galvanometer. It consists of a coil of several turns suspended in such a way that it can freely rotate about a fixed axis. This moving coil is placed in an external magnetic field produced by these two magnets. This magnetic field is radial, meaning the direction of this magnetic field is always parallel to the plane of this coil. A soft cylindrical iron core is placed to make this field radial and strong. This is the side view of the same diagram. This is the coil with several number of turns, and these are the two magnets producing magnetic field around this coil. When current I starts flowing through this coil placed in an external magnetic field, it will experience a torque. We have seen this in previous lecture. When current carrying coil is placed in an external magnetic field, it experiences torque and hence the coil will rotate. The formula for torque experienced by a current carrying coil placed in an external magnetic field is given as tau is equal to NIAB sin theta, where N are the number of turns of the coil, I is the current flowing through the coil, A is the area of the coil, B is the external magnetic field in which the coil is placed, and theta is angle between area vector A bar and external magnetic field B bar. As the field is radial, meaning the plane of the coil is parallel to the external magnetic field, theta will be equal to 90, as theta is angle between area vector of the coil and the external magnetic field. And area vector A bar is always perpendicular to the plane of the coil. So the angle between A bar and B bar will be 90 degree. So theta will be equal to 90 degree, that is angle between area vector of this coil and external magnetic field. We know that sin 90 degree is equal to 1. So when we substitute sin 90 as 1 in this formula, we get tau is equal to NIAB. However, the torque on the coil due to external magnetic field is balanced by a torque which is produced by the spring which is fitted to the coil as shown in the diagram. Because the counter torque in the spring balances the magnetic torque in the coil. If current I produces angular deflection phi in this coil, if larger is the current, larger will be the angular deflection in the coil, and thus larger will be the restoring torque due to this spring. So the restoring torque will be directly proportional to the angular deflection in the coil, that is phi. If we remove the proportionality sign, we have to introduce constant. K is the constant over here. So restoring torque will be equal to K phi, where K is called as torsional constant of the spring, and it will depend on the spring. As the magnetic torque, that is tau, is equal to NIB, and restoring torque, that is K phi, both are equal, we can write K phi is equal to NIAB. From this, we can get a formula for deflection phi as NIAB divided by K. So this is the formula for deflection produced in a coil when current I is passing through it. All of these terms in the bracket are constant. So the deflection produced will be directly proportional to the amount of current that is passing through the moving coil galvanometer. So by checking the deflection in moving coil galvanometer, we can detect the current passing through the circuit. This is the principle on which moving coil galvanometer works. We know that a current carrying coil produces magnetic field around it. So it behaves as a magnetic dipole, and hence we can calculate its magnetic dipole moment denoted by mu bar, and magnetic dipole moment is a vector quantity. Its magnitude is given as mu is equal to NIA, where N is the number of turns of the coil, I is the current flowing through the coil, and A is the area of the coil. When this current carrying coil is placed in an external magnetic field, it experiences torque given by the formula tau is equal to NIAB sin theta. But we have seen that magnetic dipole moment mu is equal to NIA. So in the formula for torque, instead of NIA, we can substitute it as mu. So we get torque is equal to mu b sin theta, where theta is angle between mu bar and b bar. Using the definition of cross product, we can write tau bar is equal to mu bar cross b bar. So this is the formula for torque experienced by a current carrying coil having magnetic moment mu bar, which is placed in an external magnetic field b bar. A current carrying coil behaves as a magnetic dipole, producing magnetic field around it. We know that a magnetic dipole freely suspended in an external magnetic field possesses magnetic potential energy because of its orientation in the field. So when this current carrying coil is suspended in an external magnetic field, it possesses magnetic potential energy, and hence it experiences torque tau bar and undergoes angular deflection d theta. This magnetic potential energy is given by the formula U is equal to integration of tau, that is torque, which depends upon theta, multiplied by the angular displacement, that is d theta. We have studied this formula in the chapter magnetic materials. Let us substitute the formula for torque, that is tau is equal to mu b sin theta. We have seen this in the previous slide. So we get magnetic potential energy U is equal to integration of mu b sin theta d theta. As mu and b are constants, they will come out of the integration sign, and integration of sin theta is minus cos theta. So we get U is equal to minus mu b cos theta. Using the definition of dot product, we get U is equal to minus mu bar dot B bar. This is the formula for magnetic potential energy for a current carrying loop suspended in an external magnetic field. Now let us consider two different orientations of current carrying coil placed in an external magnetic field. Case 1, if theta is equal to 0 degree, that is angle between magnetic dipole of the current carrying coil and external magnetic field is 0 degree. So we get U, that is magnetic potential energy of the coil, is equal to minus mu b cos 0, and we know that cos 0 is equal to 1. So U will be equal to minus mu B. This is the minimum potential energy. So the magnetic potential energy is minimum when magnetic dipole moment of the coil and external magnetic field are parallel to each other. Now let us consider case 2 in which theta is equal to 180 degree. That is angle between magnetic dipole moment of the current carrying coil and the external magnetic field is 180 degree. So we get U is equal to minus mu B cos 180 degree. We know that cos 180 degree is equal to minus 1. So we'll get U as equal to mu B. This is the maximum potential energy. So magnetic potential energy will be maximum when magnetic dipole moment of the coil is anti-parallel to the external magnetic field. So in this session, we have studied about moving coil galvanometer, magnetic dipole moment, and magnetic potential energy of a current carrying coil placed in an external magnetic field.